Welcome back to Talk Tensors. I'm excited for our deep dive today. Really fascinating stuff in the machine learning world. You know, it's crazy how much data we're dealing with these days.
It's really exploding, isn't it?
Oh, absolutely. And it feels like, well, think satellite imagery. We're talking about images that are just massive, gigapixel images. They're becoming the norm.
Right. And the challenge then becomes, how do you actually analyze that much information?
Exactly. That's the bottleneck. You know,
Yeah.
It's a huge computational challenge. And that's what makes this paper we're looking at today so intriguing. It introduces a clever new approach to analyzing these massive remote sensing images using LVLMs, large visual language models.
LVLMs, they're really making waves these days.
They are. And the goal here is to figure out, how can we get these LVLMs to really understand the detail in these images without, well, getting completely bogged down by the sheer amount of computation needed, or even worse, losing those crucial little details that are hidden within them.
Yeah, I see. So it's all about finding that balance between detail and efficiency, right?
Exactly. Because traditional methods, they really struggle with that. It's like you can either zoom way out and see the whole forest but miss all the individual trees, or you can zoom way in and see every single leaf on a single tree but have no idea what the rest of the forest looks like.
Makes sense. So this paper is trying to bridge that gap, to give LVLMs the ability to see both the forest and the trees at the same time, so to speak.
Right. They're essentially proposing a way for these models to focus their attention intelligently. Kind of like how you would if you were looking at a giant photograph and trying to find, I don't know, a specific person or object in the crowd.
That's a good analogy. So instead of processing every single pixel with the same intensity, they're trying to guide the model to zero in on the most relevant parts of the image.
Precisely. Yeah. And the way they do this is, well, it's pretty clever. But before we get into that, let me give you the full title of the paper. It's called When Large Vision Language Model Meets Large Remote Sensing Imagery, Coarse-to-Fine Text-Guided Token Pruning.
Wow, that's a mouthful.
It is. But it really does give you a good overview of what they're trying to do. They're basically combining this idea of using text as a guide with this step-by-step process of getting rid of the less important visual information, or pruning as they call it.
Okay, so text-guided token pruning. I'm starting to get the picture. So the text is kind of like a set of instructions telling the model what to look for in the image.
You got it. The main contribution, though, and what really sets this research apart, is how they've combined that text guidance with this dynamic image pyramid, or DIP.
Mm-hmm.
And the goal is super clear, super important. They want to maintain the essential details in these huge remote sensing images, or RSIs, while drastically reducing the computational cost of analyzing them with LVLMs.
Right, because if you're dealing with an image that's, say, tens of thousands of pixels wide and tall, the amount of processing power you need just skyrockets.
Oh, yeah. And the paper's introduction does a great job of laying out why this is such a pressing issue. Existing LVLM approaches, they just hit a wall when they're faced with these ultra-high resolution RSIs. Many of them rely on breaking the image up into a fixed grid of smaller tiles.
I've seen that approach used in other areas of computer vision, but what's the problem with it here?
Well, think about it. If your grid is too coarse, you end up losing all those fine details.
Yeah.
It's like trying to read a street sign from an airplane. You just can't make out the letters.
Ah, I see. So too coarse and you lose the trees. But then if you make the grid super fine, doesn't that just create an even bigger computational burden?
Exactly. Yeah. And that's what happens with some of these, well, less efficient approaches. Yeah. Like the authors mentioned LVA 1.5, which might try to handle a giant image with millions of visual tokens. It just becomes computationally infeasible, not practical at all with current hardware, and frankly, the time constraints most people have.
It's a classic scaling problem. The information density in these large RSIs is just so high. And LVLMs, as powerful as they are, weren't really designed to handle this kind of extreme scale.
Right. And that fixed grid approach, it's just too rigid. It's like trying to use a one-size-fits-all tool for a job that requires a much more nuanced approach.
Okay, so how do these researchers propose we tackle this?
Well, they've come up with a solution that revolves around two main ideas. Their region focus module, or RFM, and that dynamic image pyramid we talked about, the DIP.
Okay, RFM and DIP, got it. So let's start with the RFM. What exactly does it do?
All right, so the big picture problem they're trying to solve is this. How do we achieve efficient vision language understanding of these massive RSIs? And this isn't just some abstract academic problem, it has real world implications.
Oh, absolutely. I mean, think about urban planning, for instance. If we can automatically analyze satellite images of cities, we can get a much better understanding of their layout, their infrastructure. That can help us plan new projects more effectively, right?
Absolutely. Or think about environmental monitoring. We can track changes in forests and coastlines, all sorts of things. And even in disaster response, quickly analyzing satellite imagery after an earthquake or a hurricane can be absolutely crucial.
Right, right. Time is of the essence in those situations. So back to the RFM, how does it help with all of this?
The main job of the region focus module is to, well, focus. It pinpoints the key visual elements of the image that are most relevant to the text query you give the system.
So instead of the LVLM looking at every single pixel in the image, the RFM is like a filter, highlighting the areas that are most likely to contain the information it needs.
It's more like, imagine a spotlight. It shines on the parts of the image that matter most, based on what you've told it you're interested in. And it does this by leveraging the knowledge that's already stored within the large language model, part of the LVLM.
Okay, now that's interesting. So it's like the RFM is learning from the LLM's expertise.
Exactly. It's able to predict which regions of the image are likely to be important by observing how the LLM itself would focus its attention if it were processing similar text-image pairs.
So it's kind of like the RFM is learning to anticipate what the LLM is going to need so it can direct its gaze to the right spots.
You got it. And then, based on that analysis, it generates these attention scores. Basically, it's like a heat map, highlighting the important areas within the image.
Got it. So that's the RFM. Now, what about the DIP, that dynamic image pyramid?
Right. So imagine you take that original massive image and create a series of smaller versions of it, like a pyramid where the base is the full image, and then each level up is a lower resolution copy.
I'm picturing it. So each level is basically the same image, just zoomed out a bit more.
Exactly.
Yeah.
And each level in the pyramid represents the image at a different ground sample distance, or GSD. That's essentially a measure of how much area on the ground is represented by each pixel.
So the higher the GSD, the more zoomed out the images and the less detail you see.
Precisely. Now, the clever part is how they use this pyramid. It's what they call a coarse-to-fine strategy. They start by looking at the lowest resolution image, that thumbnail at the very top of the pyramid, to get a general sense of the scene.
Okay, so broad strokes first, then what?
Based on those initial attention scores from the RFM, which remember are generated using the low-res version of the image, the system starts selectively pulling in more detailed sections from the higher resolution levels of the pyramid.
So it's like, okay, the text mentions a bridge, and the thumbnail shows a possible bridge-like structure in this area. Let's grab a higher resolution chunk from that area to get a better look.
Exactly. It's like intelligent zooming. And crucially, it's only grabbing those higher resolution pieces for the regions that the text query has highlighted as potentially important. And on top of that, within each level of the pyramid, they're also doing something called token pruning.
Right, we talked about that earlier. So they're not even processing all the pixels within those high-resolution tiles.
Nope. They're using the RFM's attention scores to throw away or prune any visual information that seems irrelevant to the query. So even at those higher resolutions, they're focusing only on the parts that matter. And they kick this whole iterative process off by using a low-resolution thumbnail and an initial set of image tiles as input.
Okay, so that's how they're navigating the image itself. But how do they actually train the RFM to know what's important in the first place? You mentioned it's learning from the LLM.
Right. That process is what they call attention distillation. The basic idea is to transfer that ability to understand which visual regions are important, which is like deeply embedded within the LLM, and teach it to the much simpler, more efficient RFM.
So it's like an apprenticeship. The LLM is the master craftsman, and the RFM is the eager student.
That's a good way to put it. The LLM, after training on a huge data set of text and images, has basically learned which visual features are most useful for understanding different types of text prompts. And the goal of distillation is to transfer that knowledge to the RFM.
So it's like giving the RFM a shortcut, so it doesn't have to learn everything from scratch.
Exactly. Now, the way they actually do this is they feed both the RFM and the LLM the same multimodal data, both the image and the text. And then they use these mathematical tools, things like Kullback-Leibler divergence and mean squared error. These essentially force the attention scores produced by the RFM to match those of the LLM.
So it's kind of like nudging the RFM's focus to match the LLM's understanding. Look here, not there.
You got it. Yep. And they're very careful about which layers within the RFM and the LLM they use for this alignment. It has to be done in a way that ensures a smooth transfer of knowledge.
That makes sense. You wouldn't want to overwhelm the RFM with too much complexity. Okay, so we've got our trained RFM, our DIP. How does this all come together when you actually want to analyze a new gigantic RSI with a specific text query?
That's the inference process, the actual using of the model.
Huh?
And as we mentioned before, it's an iterative process. They start at one of the lower resolution levels of the DIP, and the RFM examines those visual tokens, those small image elements. And based on the text, it gives an attention distribution, basically highlighting the areas that could be important.
Okay, so first glance, figure out the likely hotspots.
Right. Then, based on those attention scores, the system makes a decision. Either one, it grabs more detailed image tiles from a higher resolution level, basically zooming in on those interesting areas. Or two, it starts pruning tokens right there at the current level, getting rid of anything that seems unimportant.
So the attention scores are really guiding both the zooming and the pruning.
Exactly. And the RFM is also responsible for figuring out where those important tokens actually map onto the original full resolution image. That's how it knows which higher res tiles to grab if needed.
Gotcha. So it's not just saying this area is interesting. It's saying this specific set of pixels located here on the full resolution image is worth looking at more closely.
You got it. And there's also a limit, which they call Nmax, on the number of potentially interesting tiles that the system will select at each level.
Why is that?
If it finds too many interesting areas at a given resolution, it's a sign that it might need to prune some tokens at the current level before moving to an even higher resolution. This prevents it from getting bogged down in too much detail too early.
Makes sense. It's about finding that sweet spot between seeing the forest and the trees. So how do they test all of this? I mean, you need some pretty hefty data sets to evaluate a system like this.
Right. And they actually realized that existing benchmarks for LVLMs in remote sensing, they weren't really cutting it.
Yeah.
There just wasn't enough variety in the types of questions they asked. And the images often weren't big enough to really push these models to their limits.
So they made their own benchmark.
They did. They created something called LRS-VQA, which stands for Large Remote Sensing Image Visual Question Answering.
Catchy. So this LRS VQA, it's like a testing ground specifically designed to evaluate how well these models can handle those really massive RSIs.
Exactly. And it's a pretty impressive data set. Over 7,000 question and answer pairs covering 8 different categories. And some of these images, they're huge, up to 27,328 pixels in their longest dimension.
Wow, where did they even get all those images?
They pulled them from 3 existing data sets, all pretty well known in the remote sensing world: FIR1M 1.0, GLH Bridge, and STAR.
Okay, so solid sources. What about the questions themselves? How did they come up with those?
They had a pretty clever approach for that, too. They used existing object detection labels, but then they created these unique references to specific objects in the images, like the northernmost airplane or the longest bridge.
So it's not just, is there a bridge in this image? It's, tell me about this specific bridge.
Exactly. And then they used GKT4V, another really powerful model, to generate these relevant and challenging question-answer pairs about those specific objects. Some of the questions are about simple things, like color or shape, but others require some actual reasoning about the scene.
So it's really testing the model's ability to understand the image in depth.
Oh, absolutely. And to make extra sure that they were really pushing these models, they used another advanced model, Qwen2VL, for a visual-centric quality check. Basically, they wanted to be certain that using higher resolution images actually made a difference in answering the questions.
So no point in having a super high-res image if it doesn't actually help you understand the scene better?
Right. And they ended up with 8 really diverse question-answer types. Everything from counting objects to figuring out their status, like whether a car is parked or moving. There are even questions about classifying areas as rural or urban and understanding the context of a specific target.
So a really comprehensive benchmark. What did they find when they tested their method on it?
Well, the results are pretty impressive. They show that their approach consistently outperforms other state-of-the-art high-resolution methods. And that's across 4 different data sets.
Okay, so it's not just a fluke on one particular data set. That seems to be a genuinely more effective approach.
Right. And they compare their method to other techniques that also try to reduce the number of visual tokens. And again, theirs came out on top, especially when dealing with those really high-resolution images.
That's compelling evidence that this targeted pruning guided by the text query is a really powerful strategy.
It is. They also found that their new benchmark, LRS-VQA, is actually tougher than an existing benchmark called MME Real World RS, which, well, just further highlights how effective it is in really pushing these LVLMs.
Makes sense. If you're trying to advance the state of the art, you need benchmarks that really challenge the current models.
Exactly. And they did these ablation studies, which means they tweaked different parts of their method to see how it affected the results. And that led to some interesting insights. For example, they found that in these really large RSIs, where you often have tons of background information that's irrelevant, pruning a higher percentage of tokens actually improves performance.
That's counterintuitive. You'd think more information is always better.
You would, but it turns out in these cases it's not. If you can get rid of all the distracting noise, the model can actually focus better on what's important.
Makes sense. So it's like decluttering your workspace so you can concentrate on the task at hand.
Right. And they also found that dynamically deciding when to stop going to higher levels of resolution in the DIP, that was also crucial for balancing accuracy and efficiency. Not every question needs the highest possible level of detail.
Right. Sometimes you just need a general overview, and sometimes you need to zoom in on the fine print.
Exactly.
Yeah.
And they also experimented with different ways of pairing layers between the RFM and the LLM during that attention distillation process. And they found that the specific choice of layers can actually make a noticeable difference in the overall performance.
So it's a delicate balancing act. Too much complexity, and the RFM gets bogged down. Too little, and it doesn't learn enough from the LLM.
Right. And importantly, when they visualized where the RFM was focusing its attention, it was clear that it was doing exactly what it was supposed to be doing, highlighting the image regions that were most relevant to the text query.
Okay, so we've covered a lot of ground here. But to really appreciate the impact of this research, I think it's helpful to put it into the broader historical context of, well, LVLMs and remote sensing.
You're right, it's all part of a bigger picture. And I think it's safe to say that the advancements in large language models in just the past few years have been absolutely astounding. And this has paved the way for the emergence of these incredibly powerful LVLMs that can, understand both text and images.
And at the same time, we've seen this explosion in high-resolution satellite imagery. I mean, the amount of data we're collecting about our planet is just incredible.
It is. And that's created this urgent need for tools that can analyze this data intelligently. And the paper does a good job of summarizing the existing approaches for dealing with high-resolution inputs in LVLMs.
Right. We've got those grid-based methods where you divide the image into smaller tiles, and sometimes they add padding around those tiles to try and preserve some context.
Right. And then there are those multi-branch approaches where you basically have multiple parallel pathways for processing visual information. And even these more complex visual chain of thought methods, where the model tries to reason step by step through the visual information.
But, as the authors pointed out, these existing methods, they often struggle when you throw those truly massive RSIs at them. They either lose detail or they just become computationally impractical.
Right. It's like they weren't designed for this scale of data. And then you've got all the research that's been done on reducing the number of visual tokens that transformers and LVLMs need to process.
Right. People have tried pruning tokens in the vision part of the model and the language part, and even these collaborative approaches that try to integrate both.
But applying these existing token reduction techniques to large RSIs, well, it's tricky. You run into issues like it can take forever to go through all the predefined grid tiles in a massive image. And if you only look at the visual information, you miss out on the guidance that the text can provide in terms of identifying the important foreground regions. And if you try to feed the LLM this huge sequence of visual tokens, you can easily exceed its input capacity, which leads to just massive computational costs.
Yeah, all those attention mechanisms, they really start to bog down when you're dealing with that much data.
Yeah.
And the paper specifically mentioned LMNE and flex attention as examples of collaborative approaches that try to improve efficiency. But they pointed out that they, too, have limitations when it comes to handling extremely long sequences or achieving really high resolutions.
So it's clear that this is an active area of research with a lot of really clever ideas being explored.
Okay, so let's recap. What are the key takeaways from this paper?
Well, I think the most important one is this. They've created a method that strikes a really good balance between preserving the critical visual details in those massive RSIs and keeping the computational cost manageable.
Right. It's not just about brute forcing the problem with more processing power. It's about working smarter, using the text to guide the visual analysis.
Exactly. And that new LRSVQA benchmark they created, that's a really valuable contribution too. It's going to help researchers develop even better models for this increasingly important area of remote sensing.
Definitely. It's always exciting to see new benchmarks that really push the boundaries of what's possible.
It is. And one more thing I found really interesting is that their approach seems to be quite adaptable. They mentioned getting good performance with different base LVLMs, so it's not tied to a specific architecture, which is great.
That suggests it has the potential to be widely applicable.
It does. Now, this brings us to our novel notions segment, where we like to, well, speculate a bit. We take the core ideas from the paper and brainstorm some potential directions for future research.
All right, always fun to think outside the box a bit. So where do we start?
Well, one idea that struck me is this. Could we apply this coarse-to-fine text-guided approach to analyzing video data? I mean, think about drones or multiple synchronized cameras capturing huge areas over time.
Oh, interesting. So instead of a static image, you're now dealing with essentially a continuous stream of high-resolution spatial information. That adds a whole new layer of complexity.
It does. But imagine if you could ask natural language questions about events happening in that video data. Like, show me all instances of cars running red lights in this intersection between 3 p.m. and 4 p.m.
That would be incredibly powerful for traffic management, urban planning, all sorts of things.
Exactly.
Yeah.
But it would require some significant extensions to this method. You'd need to adapt the RFM to understand not just where to look in the image, but also when to look. You'd need a temporal dimension to the attention mechanism.
Right. And the DIP, that dynamic image pyramid, you'd probably need to extend that to incorporate the temporal dimension as well, maybe a pyramid of video clip lengths or frame rates.
Right. Lots of challenges, but the potential payoff is huge. It could be a game changer for smart city applications, security, you name it.
Absolutely. What about your second notion?
All right, so this one's a bit more conceptual. It's about how the RFM's attention maps are used. Right now, they're mainly used for this hard token pruning. You know, if a token gets a low score, it's just gone. But what if we use those attention scores as a form of soft spatial grounding for downstream reasoning tasks?
Okay, I'm intrigued. So instead of just discarding the information from those less important regions, you're suggesting we keep it, but maybe give it less weight in subsequent processing.
Exactly, because even those tokens with lower scores, they still contain spatial information. And that information might be useful for understanding the overall context of the scene.
I see. So it's not just about identifying the most important objects, but also about understanding the relationships between them, even if those relationships are less salient.
Right. Imagine you're analyzing a satellite image of a coastal area, and you ask, what's the potential impact of rising sea levels on this region? Even those tokens related to, say, low-lying vegetation or areas that are slightly further inland, those might still be relevant for understanding the overall impact.
Makes sense. You're not just looking for the coastline, you're looking for everything that might be affected by changes to the coastline.
Exactly. And this could be really valuable for things like environmental impact assessments or predicting how land use patterns might change over time.
This is great stuff. Of course, these are just, speculative ideas, but they really highlight the potential for future research building on the foundation laid by this paper.
Absolutely. I think the big takeaway is that we're still just scratching the surface of what's possible with these large-scale vision language models. And as these data sets keep growing, the need for efficient and intelligent processing is only going to become more critical.
It is. And this research shows that we're on the right track. Using text as a guide to focus attention, it's a really elegant and powerful solution. And the new LRSVQA benchmark is going to be instrumental in pushing this field forward.
It is. And it leaves our listeners with a thought-provoking question. How are we going to keep up with this explosion of visual data? How are we going to build systems that can truly understand it and do it in a way that's both efficient and meaningful?
That's the million-dollar question. But research like this gives us hope that we're moving in the right direction.
It does. And as always, the link to the paper is down in the show notes or description. Thanks for joining us on this deep dive.
It was a pleasure. Until next time.